Okay, so if we have complex valued solutions, make sure I'm not too far over on the board, and let's see if we can get the camera to focus. Come on, camera. The one you're looking at on Zoom is focused, but this one doesn't seem to want to be. Okay. Okay, when you have complex valued solutions to your eigenvalue equation, they come in complex conjugate pairs in such a way that your real valued, or the real part of your solution is one solution, the imaginary part is another solution, and all that's completely compatible with the eigenvalue solutions. Okay, so let's just go through the process. And I'm going to shortcut the process, but we've got xy prime equals 6, negative 1, 5, 2 times your xy vector. Okay, then assume that xy is a multiple of e to the lambda t, and you get the determinant of 6 minus lambda, negative 1, 5, 2 minus lambda has to equal 0, 0, so that, now let's be careful, I'm going to get 6 minus lambda times 2 minus lambda minus negative 1 times 5 has to equal 0, and the determinant is not a vector. Determinant is 0. Okay, so that multiplying this out carefully and correctly, I hope this time, we're going to get lambda squared, and then we're going to get negative 6 and negative 2 lambda, which is negative 8 lambda, and then we're going to get plus 12. Plus 5 equals 0, so lambda squared minus 8 lambda plus 17 equals 0, so that lambda is negative 4 plus or minus 1/2 times the square root of 8 squared is 64, 4 times 17 is 68. We're going to get negative 4. So we're going to get negative 4 plus or minus I, complex conjugate solutions. Now I think I probably did that right, but we'll see. Okay, and we're going to see rather quickly, because now when I substitute these eigenvalues in here, I have to get compatible solutions. And we want to look a little bit about at a little bit of the complex arithmetic. So if lambda equals negative 4 plus I, and now let me be sure, I had negative 4, but it's got to be negative of b over 2, and b is negative, so that's plus 4. So let's correct that right now, because it isn't going to work out if I use negative 4. You can try that and you'll see. So lambda equals plus 4 plus I. We get plugging 4 plus I into the, well, I didn't write out the eigenvalue equation. We're going to get 6 minus 4 minus I, negative 1, 5, 2 minus 4 minus I, multiplied by K1, K2 equals 0, 0. Which is then 2 minus I, negative 1, 5, minus 2 minus I. I'm not sure this is going to work, but we're going to try it. So we get 2 minus I times K1 minus K2 equals 0. And we also get 5K1. I'll write it as minus 2 minus I, K2 equals 0. I don't like that 5 there. But we'll see how it works out. It's a complex number, it's a little hard to see. Okay, so what we get is K2 equals 1 over 2 minus I times K1. Now 1 over 2 minus I, complex division, is just to remind you, I'll write out the details this one time. We multiply numerator and denominator by the complex conjugate. And that'll rationalize the denominator so we can kind of see what we have. And this is going to equal two plus I over 5, so there's a 5, so maybe we're in good shape, times K2. And times K1. And I just kind of automatically solve for K1. Okay. That's all right. Now let's see if that works in the second equation. Does 5K1 minus the quantity 2 minus I times 2 plus I over 5 K1 equals 0? Well, yeah, because 2 minus I times 2 plus I is 4 minus I squared, which is 5, and 5 over 5 is 1, and we have a minus. So we have 5K1 minus 5K1, which is a little hard to see when I was looking for it, but yes. Okay? So writing this out carefully, if K1 equals 1, then K2 is going to equal 2 plus I over 5. So it's 1, 2 plus I over 5. And then it's e to the lambda t, and lambda is 4 plus I. And now we can write this using Euler identity, which you're familiar with, and separating out the real and imaginary parts here. I can write this as 1 2/5 times e to the 4t times e to the it, which is cosine t plus I sine t. It's going to be then plus, I'm running out of room, which is inconvenient, but it's going to be plus 1 I over 5 times the same thing, e to the 4t times cosine t plus I sine t. And I am going to have to break down and either wash a board, or I think maybe I can get away with using what's left on this board. Be convenient if this thing would balance, and I can make that happen. I think it's close. Okay, so what we get is 1, 2 plus I over 5, e to the 4 plus I times t. Make sure that's not up too high. Kind of is. It's a little too high for this camera, but there it is. And let's make sure we have it on zoom. Zoom gets it all right. Okay, so this, which is same as this, let me write that E a little better. Board's a little rough over here. Okay, this equals one 2/5 e to the 4t times cosine t plus I sine t plus 1 I over 5 times e to the 4t times cosine t plus I sine t. If I now bring this, well, multiply this quantity by what's inside of each of these brackets, I get e to the 4t multiplied by we're a little over time, so I'm going to compress this. We have 1 times this and 1 times this in the numerator. So it's going to be 2 cosine t plus 2I sine t. And then it's going to be 2/5 cosine t minus, okay, okay, multiply the 2/5 by the cosine t. I'm going to multiply the I over 5 by the I sine t. And I'm going to get minus 1/5 sine t. So now I've multiplied the 2/5 by the cosine t, the I over 5 by the I sine t. And now what I want to do is I want to multiply 2/5 by the I sine t. And I'm going to run out of room, so I'm going to have to kind of fudge it a little bit here, space-wise. And then I'm going to have the I over 5 times the cosine of t. I can write that now as e to the 4t multiplied by 2 cosine t, 2/5 cosine t minus 1/5 sine t. And what I've got here, again, there's a little unevenness in the board there. That's a little hard to read, maybe. But it's 2/5 cosine t. It's just this. Okay? So I've got e to the 4t times this, and what I've done is I've pulled out the real parts of this solution. This and this. And then it's going to be plus e to the 4t multiplied by, well, let's see. I'm going to put the I out in front. I'm going to pull out the imaginary parts. I have a 2i sine t, which will give me a 2 sine t. And a 2/5 sine t plus 1/5 cosine t. Okay? Now, if I've done the arithmetic right, this is a solution. Okay? The complex conjugate of this solution would also be a solution. So e to the 4t, I times e to the 4t times this, plus, or minus e to the 4t times this. Actually, the complex conjugate would be this minus this. Okay, without, because we're over time, you have two solutions. Now notice that I haven't had to even talk about the other solution where lambda is 4 minus I. Okay? If you plug in lambda equals 4 minus I, you get the same things, but your I thing's going to be different. Okay? That's the only difference you're going to have. And you don't need the other solution. When you have the complex solutions, this is a solution. This is the real part of your solution that we got just from one of the eigenvalues. And this, everything but the I, is also a solution. So your solution set is e to the 4t times 2 cosine t, 2/5 cosine t minus 1/5 sine t. And then, I don't quite have enough room, but we'll write it out, e to the 4t times, coming around to the next line here, 2 sine t, 2/5 sine t plus 1/5 cosine t. And close the brackets. So this is the first part of the solution set. This is the second part of the solution set. And again, if I'd have used 4 minus I here, you can trace it through and see how the sine of I affects everything. You just end up with a minus I here. Okay, so when you have a complex solution, you get complex conjugate solutions. If it's two equations and two unknowns, And anytime you have a complex solution, you have its conjugate. That just comes out to the fundamental theorem of algebra. If you solve a quadratic equation, if you get one complex solution, you get its conjugate. Okay? So complex solutions always come in conjugate pairs. So if you get the solution for one of the complex eigenvalues, you automatically get the other solution. That's where it comes down to. Okay, we're 8 minutes over time. I'm going to stop. Hopefully you understand that well enough to do some of these problems.